We are live.
Hello, everyone. If you are here for Science and Nature, you are at the right place. We'll just wait maybe 30 more seconds to let people come online. Thank you for joining us again. Just a little bit of housekeeping for everyone who's watching live. There is a Q&A, so if you have any questions, you can, for the presenters, you could write it in the chat box. You may add your name, it's optional. We always love to know where you're from, so if you can let us know where you're watching, that would be great. I'm going to do a little countdown for your TV, a local TV show, before we start. So 3, 2, 1, Gabe, it's all yours. Hello, everybody, and welcome to Science and Nature Untapped, a free virtual monthly speaker series brought to you by the River Institute. My name is Stephanie Hildebrand, and I'll be your host for this evening. Before we begin, we'd like to acknowledge that most of us, or many of us, are living on unceded land and traditional territory of Indigenous people. We are grateful for the opportunity to live where we do, and we thank all the generations of people who have continued their responsibilities to Mother Earth since time immemorial. If you're interested in knowing about future events, our research projects, the education programs, you can follow us on social media by searching our handles. We are on Twitter, Instagram, and Facebook. So for upcoming Science and Nature Untapped events, we have on March 3rd, Philip Ling from Maitland Tower. And on April 7th, we have Dr. Allison Derry, who will be speaking about invasive species. And again, in case you forget the date, just remember, first Wednesday of every month. And then on May 5th, instead of Science and Nature Untapped, we'll be doing the River Institute Year in Review for 2020. So I highly suggest you mark this one down in your calendars. I think it will be really interesting, and you'll get to meet many of the people that we work with. If ever you want to make a contribution to the River Institute, you can go to www.riverinstitute.ca/donate. All contributions are welcome, and we're very grateful for them. So for tonight, we have the Graphoid team. It will be a 3-part presentation, starting with Andy, who graduated with a master's in material science and engineering from the University of Toronto in 2017. In his current position as Graphoid's VP of Research and Application Development, Andy leads product management and implements long-term strategy with respect to new and emerging technologies that advance company objectives. And then for part 2, we'll have Dr. Shriman Mipati, who graduated with a PhD degree in chemical engineering from Queen's University in 2020 and joined Graphoid Inc. in 2020. It's been a very big year for you as an environmental scientist with a focus on developing decentralized water treatment technologies. And in part 3, we have Cameron, who graduated with a master's in microbiology and immunology from Dalhousie University in 2017 prior to joining Graphoid in 2018 as a business development associate. Now, as VP Product Commercialization, Cameron is focused on a collaboration-based approach to developing commercial markets and moving the company's emerging technologies through the product development pipeline. So I'd like to welcome the Graphoid team. Thank you for taking the time to present for Science and Nature Untapped. It's all yours.
Thank you, Stephanie, for the kind introduction. It's great to be here tonight on behalf of the Graphoid team, and a big thank you to the River Institute for inviting us to speak on this platform. My name is Andy Joe, VP of R&D at Graphoid, and my colleagues joining me here today are Shriman Mipati and Cameron Rente. Our talk here tonight is on bringing emerging technologies and a decentralized approach to water treatment and conservation. First off, I'll quickly walk through the general outline of the presentation today. It'll be broken down into 3 sections, which will answer the questions: how did we get to today? What problems are we going to address and how? And lastly, how and where will our work be impactful? In section 1, we'll go over our company profile, what is graphene and its unique advantages, describe our work over the years and why we chose water treatment as our primary focus, and finally, introduce a few novel filtration components that we're excited to be releasing. In section 2, Shreeman will dive deeper into whole solution systems that we're currently designing and fabricating, and how we are incorporating all our filtration materials and technologies into those systems. And finally, for section 3, Cameron will cover our company direction and mission as a whole, describe our collaboration plans with the River Institute in the near future, and talk about a few real application scenarios where our products can make a real difference. We'll start by answering the question of how did we get to today? So Graphoid was founded in 2011 and is a graphene R&D and applications development company. We're based in Kingston, Ontario, and the background photo here you see in this slide depicts of the Graphoid Global Technology Center located in Innovation Park. So Graphoid's graphene production technology was originally developed in Singapore in collaboration with the National University of Singapore. It resulted in a patented process of producing low-cost, fuel-air graphene in a cost-effective and scalable manner. The success of this process really allowed us to start exploring various graphene applications aimed towards commercialization. And over the last year, our scope of development has really focused in on clean technologies, specifically around water and air purification. Graphoid works closely with local universities as well as colleges in conducting R&D projects and research-related activities. Queen's University, for example, which is also based here in Kingston, is one where we've had consistent research collaborations with over the years. So moving on to introduction of graphene. Graphene, which has been quite the buzzword over the last decade, is a 2D mesh of carbon atoms arranged in a hexagonal structure. This structure is the basal plane of the most common crystal form of carbon, graphite. In other words, if you manage to isolate a single atom layer thick of graphite, you've managed to create graphene. And this is exactly what scientists Andre Geim and Konstantin Novoselov did in 2004 using the Scotch tape method. However, even from that discovery, the production methods were a long way off from being scalable. The recent advancements in large-scale production of graphene, like here at Graphoid, are really what lowered the cost barrier and made it a viable material for real-life applications. Graphene, having this honeycomb-like structure, demonstrates incredibly high mechanical and electrical properties. What is relevant for water purification is its extremely high surface area and the ability to functionalize. And by functionalize, it's a chemistry term meaning to attach various chemical groups onto the surface, which can alter the contaminants the materials are capable of removing. So on the bottom right here, this is an SEM image. On the left-hand side shows an image of graphite, and the other 2 images on the right displays graphene produced by Graphoid, which we call mesograph. The mesograph material, by comparison, is very thin and uniform, and naturally you start to lose that roughness of the material surface you see in the images. So moving on to graphene synthesis and production. Here at Graphoid, we use graphite as a starting raw material, which we then employ chemical, mechanical, and electrochemical processes to exfoliate the graphite into graphene. One distinction I'll clarify here is the difference between graphene oxide and graphene. Graphene oxide has oxygen groups introduced during the production process, and these are distributed throughout the structure. The incorporation of these new oxygen groups lead to very big differences in the final material characteristics. For instance, graphene oxide is hydrophilic, meaning it has a high affinity for water, while regular graphene is just the opposite. It's completely hydrophobic. So both of these materials are very important in water filtration and is really the backbone for all of the different adsorption materials we create here at Graphoid. So to summarize Graphoid's processing advantages, it's cost-effective, environmentally friendly, creates a high quality, low layer count product, and is most importantly very scalable. And because of the potential use of graphene is so vast, our original R&D areas were really quite scattered and ranged from energy storage to membranes to composites and to coatings. What we found was that it's not really possible to do it all, but rather focusing on specific applications would give us the best chance at commercialization. So in 2019, we had a lot of external confirmation that these materials that we were creating had large impacts in the water sector. And in 2020, we made the decision to focus on water purification specifically. And going forward, we plan to leverage the graphene expertise we have here at Graphvoid to create novel and disruptive water filtration materials, pursuing our mission of making clean and safe water accessible to all. So here's where we start getting into the really interesting part. One of the first and most important products we have pushing forward is the G10 graphene cartridge, which we are planning to release this quarter into the market. This cartridge is intended for drinking water use and is a blend of graphene media, which really pushes the envelope in terms of filtration efficacy. The materials are designed specifically for heavy metal contaminants, such as mercury, arsenic, lead, etc. And even in Canada, where drinking water is relatively abundant, the heavy metals issue can still arise. For instance, arsenic and iron present in groundwater, as well as lead contaminations from old piping infrastructure, all of which can negatively impact human health in both the short and long term. These materials have been individually certified by the NSF for drinking water safety. NSF 61 is the standard, allowing it to be used for residential customers as well as municipal treatment facilities. So in comparison with conventional activated carbon, the G10 materials are on average roughly 20 times more effective in removing heavy metal contaminants. The left graph here is the graphene filter, and on the right is the conventional granular activated carbon filter, which you'll find in a product like Brita filters. The graphs display the input and output concentrations of each contaminant after passing through the cartridge. And in comparing the two different materials, it's clear that the output concentration from graphene filters is really close to zero, while for GAC, the output concentrations can be a lot higher, and in some cases, even higher than the EPA standard. So these adsorbent materials are very suited for removing dissolved contaminants. And moving on to the next slide, we'll introduce filtration technology targeting undissolved solids, including biological contaminants. Here we're introducing ultrafiltration. So ultrafiltration is a method of separating solids and liquids using something called a hollow fiber membrane. Each filter has hundreds of these hollow fibers contained within, which allow the passage of water. Only clean water can pass through the pores in the fiber, which acts as the primary filtration mechanism. All of the particulates, the UF membranes, the pore size can range from between 5 nanometers to 100 nanometers, depending on the product. And the particulates, whether it's sand or silt or bacteria and viruses, can be filtered if it's larger than these pore sizes. The filtration process occurs at low pressures, and a built-in backwash capability allows for a long service life product. So this is an existing technology which is used quite extensively in wastewater treatment. And here at Graphvoid, we're collaborating with UF membrane manufacturers to push this one step further by incorporating nanomaterials directly into each fiber, drastically improving the filtration performance. So here we're showing a comparison table between ultraviolet disinfection technology, UV, which is really popular here in North America, versus ultrafiltration. When we start talking about 10 nanometers or less pore size products, the ultrafiltration filters have an extremely high filtration rate in comparison. And so some of these advantages I'll highlight here are the ability to operate without electricity. The UF filter functions independent of water pressure, flow rate, or turbidity, which we can't say the same for UV technology. And finally, the lifespan of UF filters can be as high as 3+ years. So these are some of the reasons why this is a major component for us when we start designing complete systems for water treatment applications. And to introduce that aspect, I'll hand over the mic to Shreeman, who will cover section 2 of this talk.
Thank you, Andy. Thank you, Andy. Hello, everyone. As Andy mentioned, our company is focused on several graphene-based technologies. However, in this presentation, I'm going to talk about the different problems related to water treatment and how we are going to address it with our advanced technologies, specifically related to the portable and decentralized water treatment systems. We focus on such systems for two main reasons. First of all, they are easy to carry anywhere, including remote locations. And second, to take the advantage of using graphene to enhance these treatment capabilities. To achieve this, our company developed products by integrating several of our proprietary components. So in the next slide, we can actually see what are our products here. So currently we call our water treatment products as compact filtration systems, simply called CFS. And we have designed and developed 3 versions of CFS, V1, V2, and V3 for various applications. And here we call them simply V1, V2, V3, and hopefully our company marketing team will come up with catchy names in future. But for now, let's stick to V1, V2, V3. Coming to CFS V1, shown in the figure on the right side, it is a portable lightweight system having 3 major units for water treatment. First one is the mechanical strainer, which removes the grit and suspended material. And the second one is the graphene and activated filters, which removes the naturally occurring heavy metals, which Andy spoke in detail. And also the third one is the ultrafiltration unit, which has an average pore size of 10 nanometer, will assist as a tertiary treatment to remove microbes and bacteria. That means the final treated water that is coming out of this unit is NSF certified high quality drinking water. So this can be used for any kind of human consumption. And we have already developed a prototype and tested its performance using synthetic water with added pollutants and also surface water from lakes and ponds. So the results showed removal of all contaminants and also a 6-log reduction in microbes that you can see in the figure on the right side. And coming to the size and specifications, as you can see the size, it can fit in back of a car, and it also weighs about 56 kilograms that can easily handle by a single person, because it has these wheels we can carry like a luggage bag, and also it is similar to carrying a 2-gallon large bottles of water in a campsite or something like that. And this unit can operate at a flow rate of 5.5 liter per minute. That means with just a 10-minute operation in a day can produce sufficient water for drinking and cooking for a family of 4. So this shows that CFS V1 is a suitable candidate in remote locations and other kinds of places. And coming to CFS V2, that is the version 2, is a decentralized point of entry treatment system. That means the unit is a standalone system which can be fixed in each house, and where the water enters and passes through the system before entering the house. So it is a scaled up version of CFS V1 system. And this system is different in terms of it can achieve higher flow rates and also to meet the pressure requirement for different fixtures in the house. So our main focus of this unit is for treating water that is drawn from wells or surface water, or even the municipal water coming, and if there is any kind of contaminants entering the house. So in the next slide, we can see what are the different kinds of applications that we are targeting using this CFS V1 and V2. So CFS V1, that is a portable version, can be used for cleaning polluted surface waters for drinking, and in remote campsites, as I mentioned, and in military preparedness and operation camps, and also in disaster relief systems like in floods or hurricanes or monsoons, etc. And also it can be used for making bottled water to carry if we are traveling from one place to another place. And coming to CFS V2, it's a point of entry or point of use system which can be used at home. So you can use it as a point of entry just before entering the house, or you can also use it as a fixture to a kitchen or even for drinking water purposes. And it can also be used in communities or homes that may have inadequate, that may not have adequate municipal water, and also in cottages where the water is drawn from wells or something where the minimum treatment is required before consumption. So going to the next part of the presentation, till now I have discussed about the water treatment, but it's our major focus should be given towards water conservation too, because that's where we can save a lot of water. As you see in the pie chart, in a single household, the grey water constitutes major portion, that is almost like 65% of water that we consume. And this water includes the water coming from kitchen, laundry, sanitation, etc. And here the major pollutants present in this grey water are oil and grease coming from the kitchen waste, surfactants present in the bath soaps. These are not easily removable pollutants in a single step process because of their variety and complexity in composition. If this water can be treated and recycled back, this will be really advantageous for each individual house or community. But to achieve that, we have to reach a minimum criteria, which you can see in the table, that is NSF 350 standard before reusing in the house. So there are several technologies that are currently available in the market to treat at a community level, but as a household level, there are still few technologies which are operating and for utilizing the grey water. But our technology that I will be discussing in the coming slides can maximize the treatment capacity in more economical way. And another major focus of our technology is not just reusing for some kind of without human consumption, but our target is to achieve NSF 61 standard for drinking water. And in the next slide, we can see how we can use this recycled water in the houses. So the treated grey water can be used for different applications, which is like NSF 350 standard for toilet flushing, gardening or landscaping, floor mopping, car wash. However, we aim to bring it to NSF 61 standard, where we can use it for cooking, drinking and sanitation purposes as well. So these are the major applications where we can use this water. And what is the advantage of this is reducing the need for fresh water. That is the major advantage. And saving on freshwater use can significantly reduce household water bills, but also has a broader community benefit in reducing the demand for public water supply. At the same time, reducing the amount of wastewater entering the sewers because we are producing less waste as we are treating it. Again, this can benefit the individual household and also the broader community. Another major advantage is the heat consumption, where it reduces the stress on hot water boilers as the temperature is maintained because the unit is inside the house, like in a basement or garage. And it can also reclaim the nutrients from water when it is used for gardening or landscaping. So these are the major advantages and applications. So in the next slide, we can see how we can actually, where we can actually install this kind of system and what kind of treatment systems are available. So here you can see in a house, in a decentralized system, such as household if we take for treating grey water, the water treatment system is where it is shown in the dotted box. That's where it can be fixed. So the flow diagram shows how water goes in and out of this system. So here we can see that the grey water is collected in grey lines from different fixtures coming into the water treatment system. And then the municipal water entering the house to compensate the needs for direct consumption. Like if there is any failure of the system, still there is a connection which is directly coming into this. And then it is resupplied to the house, which is shown in the green lines. So with our design, we are aiming to achieve the NSF standard drinking water so that we can further improve the quality and quantity of reusable water. That's our target. So as I previously mentioned, there are several technologies available, but some of them are like advanced oxidation bioreactors in combination with tertiary treatment units. But the upcoming technology, which is the electrochemical treatment system, which we are developing in our company, is an upcoming technology, and it has much more benefits and advantages than existing conventional treatment methods. So in the next slide, we can see what is actually an electrochemical treatment system. So there are several kinds of electrochemical treatment systems like electrocoagulation, electrooxidation, flotation, ultrafiltration. In all these methods, the common thing is a presence of a positive and negative electrode, and where one of them becomes as a sacrificial electrode depending on the type of treatment, and the choice of electrode material is the booming research topic in academia and industry, as this is the best treatment method that a lot of companies and also in a lot of community level scale water treatment plants are implementing. So the figure shows a schematic of electrocoagulation and adsorption for arsenic remediation in India. Here, as an example, I'm showing one big contaminant, that is arsenic, which is most prevalent in India and Bangladesh, and also not only in India, it is also there in Canada, in US, and in many parts of the world. And for this particular contaminant, electrocoagulation has been chosen the best treatment method. So here you can see that from my previous work, where I worked in designing and installing a 10,000 liter plant in collaboration with UC Berkeley. So what we did there is, when you have electrochemical reactor and we have this set of iron plates arranged in parallel direction, parallel to each other, with alternate positive and negative electrodes connected to a DC power supply. And when a required amount of current is passed through it, the anode material, which is sacrificial, oxidizes from Fe0, that is iron, to Fe3 or Fe2, and then these forms the ferric iron oxides, and these have this property of surface where it can absorb these arsenic ions that are present in the water onto the surface. So it's basically a surface adsorption process. And once this gets absorbed, later these particles settle down and can be separated out by conventional sedimentation process. And what is this process unique from other things? That is, like during this process, one unique advantage is there is arsenic-3 in the system, which is not easily removable by conventional methods. But in this system, the in situ process has this capability of oxidizing this arsenic-3 to arsenic-5, which is the one that gets absorbed onto the surface, which is not possible in conventional treatments. So this makes this system very unique. And so this shows that this technology is not only applicable for just heavy metals, it can be implemented to other kinds of contaminants, which we see in grey water. So this system can be extended to grey water, where the composition of water contains chemical oxygen demand, biological oxygen, surfactants, oil and grease from kitchen, and also the microbial waste. So it basically can treat most of these things with just basic modifications like changing of electrode or a combination of introducing different kind of technology combination with this. So in our technology, we are designing a treatment unit that combines these techniques in reducing the footprint of the unit along with the performance enhancement and producing the NSF drinking water standard quality of water. So in the next slide, you can see the CFS V3, that is the version 3 of our system for treating grey water. This concept of electrochemical treatment system that I just previously discussed, that we are going to integrate into the overall system. Here you can see that there are 3 modules, and it just mimics a conventional treatment plant at a community scale, where you have primary treatment, secondary treatment, and tertiary treatment before it goes for distribution. So this basically fits into a house or a small community like a old age home. So here you can see that in CFS V3 flow diagram, the treatment happens in 3 modules. In module 1 is the primary treatment for removing grease and particulate matter. And module 2 is the secondary treatment, where we use our novel electrochemical technology, which is a combination of electrocoagulation and electrooxidation happening in the same tank, and followed by a rapid sedimentation of pollutants. And in module 3 is a tertiary treatment, where we have the filters that we previously discussed, like CFS V1 and V2, which removes most of the remaining compounds, if there is any, and brings to a 6-log reduction in bacteria, if any present. And finally, the treated water can be reused for various applications in the house. Additionally, there is a little concentrated waste generated during this operation that you can see in these figures, like sludge collection and concentrated waste that is coming from food and the oil and grease inceptor. So what we can do with this, there are 2 ways. One is, these are basically just the concentrated form of the waste that we generate in the house. So it can be directly released to the sewer just in a very low volume. Instead of sending 100 liters, we send 3 liters. And or it can be used as a byproduct in house construction for making bricks, or even road construction or something like that. At the same time, the concentrated waste that is coming from the oil and grease is basically, for a long time, this has been used as food for cattle, or it is used as a manure. And these are the major applications. And our target for this product is to make it a turnkey project. That's the whole idea. So we made it in 3 modules, put it into together in a house, and with a low maintenance, yearly maybe once or twice. And we are also making this process fully automated with smart features. So, and this technology does not limit to just single households. This can be scaled up for community treatment, old age homes, apartment complex, for industries with minor changes in design and materials, like in mining industry or something, where like vast majority of industries. And additional safety features are provided to bypass from municipal wastewater, and several smart features are also included to make this user friendly. However, there are still some challenges that we are facing or need to face to bring these products to the market. And here I hand over the mic to Cameron, who will cover the impact and our outlook of our company in section 3 of this talk.
All right. Thank you very much, Sriman and Andy before me, for the fantastic presentation so far. And thank you as well, again, to the River Institute for hosting us at this event. So now that we've gone through the technology overview so far, I'm going to discuss more about the forward-looking impact section of the presentation. And I'm hoping that this will lead the audience to better understand why we've engaged the River Institute for collaboration, and also to introduce what we hope to accomplish with these technologies in the future. And I'll do that through looking at a few case studies that summarize the key areas where the impacts will be felt. So I'll move on to the next slide. And the short answer to why we have engaged the St. Lawrence River Institute is that we do truly need to study the exact effectiveness of our CFS version 3, the system for gray water recycling, and its component technologies within the context of residential gray water. And the River Institute is perfectly suited to help us do that. So the ever-changing climate that we're currently faced with, as well as increasing pressure on water treatment infrastructure at centralized locations in municipalities, has led to evolving market conditions where these types of decentralized water management systems can really play a significant role in alleviating that stress. So in order for our company to be successful in implementing a solution to this problem, it's really critical that we have our technologies assessed by an independent third-party organization at the research level, such as the St. Lawrence River Institute. So following up to that down the road, we expect successful reporting of the results will lead to opening the right doors into real-world pilot studies across Canada and beyond. So this first project that we're engaging in is really designed to be our launch platform. And going forward, our core mission is to transform the access, security, and conservation of water, as Andy had mentioned earlier on in the talk. So going on to the next slide, with respect to emphasizing on access a little bit further, we really see the CFS version 1 technology playing a major role here to help serve remote communities and locations that are not necessarily connected to a water treatment infrastructure with a cost-effective and portable technology that can produce large volumes of water and do so in a way that is easy to operate, track performance, and maintain, regardless of somebody's educational level, for example. The technology that we're using in CFS version 1 is very closely related to that for version 2, which plays a role in the security theme as well. And so there's countless examples still in Canada where either a centralized water treatment facility either encounters an issue or fails altogether. And when that happens, typically the impact on a community is devastating and even deadly. So many of the audience will remember back to Walkerton, Ontario, where there were actually deaths caused due to a centralized treatment facility failure. As we move on to conservation, and as Sriman greatly introduced in section 2, we consider water to be our most precious natural resource. But here in Canada, the usage pattern for water is often an afterthought. And so as we seek to introduce these products to the market, we want to do so in a way that is always collaborative and seeking to address a key problem area. So to extend on that a little further, we are always seeking to identify and form new collaborations with people that are interested. So please look us up in the contact information at the end of the presentation. We firmly believe that no single technology can solve the water crisis, but we have three great ones here, V1, 2, and 3, that we think can play a significant role in these three key areas. So I'll move on to the next slide here. To touch on a couple of case study topics that I'll introduce further in the next slides. And these first two in the table focused here on the left-hand side on access for version 1. I'll use the case study of the 2017 natural disaster caused by Hurricane Irma and Maria, which hit Puerto Rico and several Caribbean islands back in September of 2017. Looking at version 2 of the system as well on the right-hand side, where we're considering its application as a fixed location system at the water point of entry, we'll be able to solve problems such as what is going on at Grassy Narrows in Ontario, or what has happened famously in Flint, Michigan with the type of V2 system here. But before I dive into these case studies, I want to just emphasize several of the key performance highlights of these two systems that are consistent across all the technologies. So as Andy touched on, the adsorption column cartridges that are based on graphene materials are typically about 20 times more effective at removing heavy metal contaminants than common activated carbon filters you would buy off the shelf at a local hardware store, for example. These filters additionally will demonstrate a much longer lifetime, typically about 2 times longer than that of an activated carbon filter. And as we begin to talk about the ultrafiltration technologies, these truly are superior to UV disinfection systems, where we can attain up to a 99.9999% reduction in bacteria and 99.99% reduction of viruses without the limitations that UV technologies can face, such as what's imposed by water turbidity or very rapid water flow rates. A really important feature that we really haven't covered about the technologies yet, but that plays a significant role in our go-to-market strategy, are all of the built-in sensors and the way that those sensors, such as for flow rate, pressure, GPS, and water filtration quality, play a role in a smart sensing platform so that users, regardless of their knowledge or experience in handling water and water quality, will receive the proper notifications and insight towards their water quality, and will be able to, when required, schedule technician support, for example, to come in and do preventative maintenance on their system before, say, the natural lifetime of a filter is reached. And so I'll move on to the first case study example that I'll present for version 1, the CFS version 1, which, as I mentioned, was the Hurricane Irma and Maria disaster that happened to both hit Puerto Rico within a span of about 2 weeks back in 2017. So when this happened, the population of 3.2 million people was affected. And during a disaster such as this, water becomes the single most important quantity for preserving human life and health. In September of 2020, just recently, the FEMA Inspector General report was released that detailed the major missteps in how FEMA responded to this crisis. And what ended up happening was actually less than 27% of the communities attained sufficient water from the FEMA response. The organization spent $361 million for a total of 12 million gallons of bottled water, which comes in at about $30 per gallon. And the shipments of this bottled water took 70 days to be delivered. And overall, about 63% of the water that was shipped was actually lost. And as I move on to the next slide, there's an image depicting that here on the top right. So with our CFS version 1, we did not have it available, obviously, in 2017. But if we did, in this type of disaster relief situation, considering the certifications that the technology will attain within this year for NSF approval, we would be able to generate the drinking water for the citizens of Puerto Rico at a minimum at 4 liters per minute from any groundwater source or surface water source, such as a nearby pond, lake, or river. And looking towards the value proposition here in the bottom right, or sorry, the bottom of the slide, When producing 4 liters per day for each individual, a 3.2 million population would need a total equivalent of 12.8 million liters of water. And so to do this, we would recommend using approximately 3,000 of these CFS version 1 systems. And in solving this solution for the Puerto Rico population over the span of a full year with 3,000 systems, and this is considering the running costs for periodic replacement of the filters, overall for a span of an entire year, FEMA would have spent at least 5 times less than the 361 million that was spent for shipping bottled water to the disaster relief situation. And so moving on to the next case study for the residential drinking water situation that is still a concern in several areas of Canada. As of December 23rd in 2020, there were still 58 long-term drinking water advisories active in over 40 First Nation communities here in Canada. And just prior to that statistic, the Government of Canada announced another 1.5 billion in investments to help solve this problem and create clean drinking water with an infrastructure that can be maintained and in good condition. And so typically with a drinking water infrastructure in place, you don't see a boil water advisory or a water advisory taking place, but when something goes wrong at the facility, if there is a suspected or known to be contamination with parasites, bacteria, or viruses in the water, a boil water advisory is always going to be issued. And in certain cases, a do not consume or a do not use advisory may also come up if a chemical contamination issue has happened due to the water treatment facility encountering a problem. So in moving on to what we would apply our version 2 CFS system for, is to really create an enhanced level of security in communities and in homes across Canada that would actually be able to entirely prevent boil water advisories from ever having to take place again if there was ever a suspected contamination of bacteria or viruses due to inadequate treatment at a central facility. And for the most part, if not in many cases, with our CFS version 2 system, the do not consume and do not use advisories if a chemical contamination issue occurs would be able to be avoided as well. And so on the left-hand side, I just want to highlight the user interface for a Android or iOS familiar person using a smartphone that would have a version 2 system in place in their home. Through this platform, they will receive notifications automatically from this sensing platform so that they know when it is necessary to change filters based on the water quality being received. If water quality and treatment from a centralized location or a well is generally good quality, the maintenance on the system is very low. But if something were to go wrong and the system were to be relied upon, maintenance would be recommended 1 to 2 times per year, given normal use of water volumes. So moving on to the third version of the system, and before diving into the case study here, I think it's really important for the audience to recognize, which many of you I'm sure already do, that the water crisis currently ongoing in the world is perhaps the most important challenge faced by humankind. And the availability of clean drinkable water around the globe is so closely tied to climate change. And so for anybody who's not familiar with this, I just encourage you to watch the documentary available on Netflix called The Brave Blue World. And I've just included a quote here from the movie. But on the second point as well, another important topic to mention is that just recently in December of 2020, Wall Street actually began to trade water as a commodity, just like gold and oil. And so a quote from RBC Capital Markets stating that climate change, droughts, population, and pollution are likely to make water scarcity issues and pricing a hot topic for years to come. And that's really why we're focused on water conservation with our version 3 system. So in Canada, we're typically considered a water-rich nation, possessing about 7% of the world's fresh water. And the amount of water consumption in each Canadian household in 2009 from statistics at the City of Toronto is equivalent to about 630 liters per day in each household. Now, the number of people per house in Canada is about 2.9, and in Toronto, 2.5. And so this equates to each person using about 217 to 252 liters of water per day. So with our CFS version 3, as Shreeman detailed earlier on, which is essentially designed to mimic the quality that a municipal water treatment plant can produce, just in doing so in a small decentralized footprint that's really similar in size to a furnace or a large water heater that you would see in your basement commonly today. And so as I advance back to the next slide, the water, incoming water and output water diagram that Shreeman covered earlier in the talk, I've now added several statistics and percentages at the various fixtures within your house, such as the kitchen sink in the bottom right, the dishwasher next to that, the bathroom sinks, the shower, the washing machine, and the toilets above, where water and a specific amount of water is typically consumed within the house each day. With this water treatment system in place, what the expected outcome is exactly about up to 65% of input water being recycled within the home on a daily basis. And so it's really important within our collaboration with the River Institute to certify the quality of water to be at a very minimum achieving the NSF 350 standard, but given the nature of the technologies we've put together here, we really do firmly believe the water quality is fit for human contact coming out of the system, which is why it can be directed back to the showers and to the sinks and the clothes washing machine, atypical of common gray water solutions that are available in the market today, which typically just focus on recycling water for toilet flushing. And so as I move on to the next slide here, where we really begin to hone in on the expected impact of this version 3 system. And so going back to the statistics of about 2.9 people per household and 250 liters of water per day per person being consumed, at that rate, an average household would be able to conserve about 172,000 liters of water per year. And at the customer level, this is going to help you reduce spending on your monthly utilities bill, and it's going to reduce significantly the environmental impact that new housing developments or commercial buildings put on communities today, where typically at communities across Canada, infrastructure and sewage treatment plants are at or nearing their capacity. And so we want to be able to help out these locations and not having to spend multiple $1 million in many cases to have to renovate and retrofit existing infrastructure by creating a decentralized approach here that is very accessible in terms of data collection and very effective at treating most of the water that's contained within the house. So simultaneously to the water conservation statistics here, the homeowner, as well as we would expect the municipalities that adopt this technology, will want to always be able to ensure that the security around water quality is being maintained by tracking conservation and quality statistics, either on the mobile device or at a centralized command center type of location. And so moving on to some of the obstacles that we believe we have to overcome really to be successful and to help achieve our mission. One of the very first ones that we need to do is to continue working with our partners to develop an accessible and interactive platform for individuals across all age groups and education levels that is a way for people to bring questions and concerns about our systems and technologies to our attention. And so we can help them better understand exactly the significance of the impact here. Within the context of gaining the proper approvals from municipalities and local government to accept these technologies as advanced and modern solutions to the aging infrastructure and sewage treatment capacity problems, we really foresee these types of organizations being critical partners for us in the future, especially from a data collection and management perspective, to ensure that the quality is being maintained. We know that our expertise typically is on the engineering and materials side, and not necessarily the servicing side of the coin here, but that is equally important to developing an effective solution that works initially is to maintain that solution. And so training service personnel and creating in many cases, a community-specific operating budget to help the communities adopt this technology as a more cost-effective and environmentally friendly approach to preserving water infrastructure and their local environment is extremely critical. And that's part of our major focus as well as we go forward, is to develop these educational tools. And so last but not least, one of the huge challenges that we face is pushing social acceptance behind the efficacy of these technologies. So in Canada, typically when something goes wrong and people don't trust that their water is clean, bottled water becomes the fallback or fail-safe mechanism for cooking and consumption. And so we really aim to change that mentality with a system that interacts directly and proactively with its users, so that they can be confident that the water they're receiving at their taps is extremely clean. So we're very excited with the collaboration here as we go forward and summarize the presentation to work with the River Institute and gather the proper data that really validates our claims behind version 1, 2, and especially the newest technology, version 3, as we put them to the test. This will really enable us to attain the proper NSF certifications as we go forward, while our materials and systems are believed and understood from our own data collection to be compliant to all of these certification standards. It's very important to still conduct the third-party certification here as these enter the market. And it's extremely important as well to prepare the right type of educational publications and documentation on a product-by-product basis with the help of the River Institute to bring these technologies to market. As I said earlier, we're open to new ideas for collaborations going forward. So if anyone would like to reach out to us, please find our contact information on the next slide. And as I said before, I just want to reiterate that the access, security, and conservation of water in communities across Canada and beyond is where we're going, and really believe that our material science history in developing these graphene-based technologies can help us to get there. So with that, I just want to say thank you again to the River Institute for hosting us, and I will turn the microphone back over to Stephanie.
Hi, thank you, Cameron and Shreeman, Andy. Especially the case studies, I think it puts into perspective the importance of clean water, but also conserving water. So thank you for the work that you're doing. And also thank you for presenting tonight. I do have a couple questions from the public for you. The first one is, does this material remove chemicals that can form hydrogen bonds from water?
I believe the answer to that is yes, based on all of our testing. Perhaps better suited to answer might be Andy or Shreeman as the folks who wear the engineering hats at our company.
Yeah, so I'll kind of take this question on. As I mentioned before, some of our graphene materials, the key here is really on functionalizing the graphene. So depending on kind of which chemical groups you attach to the surface, it can very much, you can kind of tailor the material for the contaminants that you're looking to remove. So in terms of hydrogen bonding contaminants, definitely as a absorption mechanism, you can remove the specific contaminants that you're looking to remove. But in terms of, you know, a specific contaminant, you'd have to do kind of trials and testing to make sure that it does do what it claims to be doing. Yeah.
Great, thank you. And the second question is from Marco Vincelli. He asks, our experience with ultrafiltration cartridges in municipal applications, so more than 8,000 MLD, is that their service life is around 7 years. What is the expected service life for your UF membranes?
So I'll take on this question as well. So typically what we've seen so far is at least 3 years in terms of service life for our UF membranes. But like I said as well, we're really pushing the envelope in its performance by adding nanomaterials to the filters and the hollow fiber membranes. And what this will end up doing, what we hope, is also improve the anti-fouling aspect of the ultrafiltration filters, which will greatly improve its lifespan. And yeah, 7 years or even longer, I think is definitely possible.
Great, thank you. And Lee is asking, so thank you for the great presentation. And the question is, for a homeowner that currently uses well water, how much could the system cost and how often would it need to be serviced?
Yeah, so just touch on frequency of servicing first. That really does depend on the quality of the well water. In most cases, groundwater in Canada is pretty good quality, but certain locations have to watch out for heavy metals like mercury and arsenic in the water. So it's important to have your water tested so you know exactly what you're dealing with. And with respect to pricing, our company is really undergoing a significant transition at this time. So unfortunately, I'm not going to disclose that publicly at this time, but would definitely encourage you to contact us for more information and be happy to follow up with you directly about the pricing question.
Great, thank you. And we have a question that maybe I'll be able to answer, but I'll also leave you guys the opportunity. So Tom Olian is asking if the slides are available, or at least a list of the suggested links to Netflix and others. So Tom, all of our Science and Nature Untapped events, we share it on YouTube. So if you were to find the YouTube for River Institute, there's a playlist for Science and Nature. And you should be able to find this whole presentation and watch it all over again. Otherwise, do you guys have any input for that?
Yeah, if you'd like to just jot down the email address there very quickly. If it's not easily accessible online, like Stephanie suggested, we'd be happy to send the package to you directly.
Great, thank you, Cameron. And we have one more question here. For a V3 unit in a standard house, what is the projected reduction in water use and what is the power consumption?
Yeah, that's a great question. I'll maybe ask Sriman to comment on the power consumption perspective, but the expected conservation is up to 65% of what you would see in your monthly utilities bill would be eliminated by this technology. So you're reducing your water volume consumption by 65%.
Great, thank you. So we don't have any more questions at the moment with 3 minutes left, so I suppose the timing is quite good. If we do have questions come in, we could continue, but for now, I'll just say goodbye to everybody who's watching Science and Nature Untapped from your TV. Thank you again for joining us. And also don't forget about in May, we'll have our year in review, and I think it will be an excellent opportunity for you to meet the team at River Institute from your homes. So thank you again for watching. And I suppose for everybody else, I don't have any more questions coming in. So maybe we'll wrap it up now. So I just want to thank you on behalf of the River Institute for taking the time to join us today. I think we're very excited to see where graphite goes and the projects with River Institute. So thank you again. And thank you to everybody watching us live, and thank you for supporting us. And also the next live event is March 3rd with Philip Ling, and then on April 7th with Dr. Allison Derry, who will be speaking about invasive species. So thank you very much and have a good night, everyone.